Alright, in this video today, I'm going to talk about and go through an example of how you proportion a concrete mix design. So before you start designing a mix, you need a application for your mix. So we're going to design 4,000 psi concrete for a pedestrian bridge at the College of New Jersey. Since it's a bridge and it's outside, it's going to be exposed to freeze and thaw, and we're going to have to put some type of de-icing agent on it once in a while. Actually, this winter it's probably been more often than once in a while. The concrete is going to go into the slab. We're going to say the slab is 6 inches thick. The rebar has a minimum spacing of 2 inches. It has a minimum cover over and under the rebar of 2 inches. And it's important for us to say that we've never made this mix before because, like I told you many times, to really understand a concrete mix, we really need to understand the statistics about it. Since we don't understand the statistics, we're going to have to modify our mix design. So once we've decided what kind of mix we need to design, we can then start looking at our materials. And materials are you're kind of stuck with the materials you have in the region of the country you're in. Cement is universal, but coarse aggregate and fine aggregate change throughout the country. What's available, what's not available. So when you're doing a mix, it's important for you to understand the properties of the different materials you're going to put in your mix. So a lot of the early on work in proportioning a mix is figuring out what your material properties are, what your aggregate properties are. So the properties you need to understand for the coarse aggregate are the bulk oven dry specific gravity, the absorption, the density, and the moisture content. For our mix, we're going to use number 57 stone, which is a crushed stone that has a nominal size of 3/4 of an inch. To determine the bulk oven dry specific gravity and the absorption of the aggregate, you use ASTM C127. To determine the density of the coarse aggregate, you use ASTM C29. And to determine the moisture content, you use ASTM 566. With the fine aggregate, you still need to know the bulk oven dry specific gravity, the absorption and the moisture content, but you also need to know the fineness modulus. The bulk oven dry specific gravity and the absorption are found using ASTM C128. The moisture content is found using ASTM 566, and the fineness modulus is found using ASTM C136. The fineness modulus is found by doing a sieve analysis. What it tells you is pretty much how much fine aggregate you're going to be able to fit in between the voids of the coarse aggregate. The more fine the sand is, the more sand will fit in the voids. Alright, once we know our material properties, we can actually start proportioning the mix. The place we start is with the strength. We decided we wanted to design 4,000 psi concrete, but we've never made the mix before. So we don't know if we design for exactly 4,000 psi, we're going to get 4,000 psi. Since we've never made the mix before, even once, we're automatically going to have to increase the strength by 1,200 psi. So instead of designing a 4,000 psi mix, now we're designing a 5,200 psi mix. So our whole mix design will be for a 5,200 psi mix, in the hopes that it will ultimately give us more than 4,000 psi. Once we know what strength we're actually designing for, we need to pick our water-cement ratio. So to pick water-cement ratio, you look at table 7.1 in your book, and it gives you the relationship between water-cement ratio and the compressive strength of concrete. So on the right-hand side here, I have a copy of table 7.1, and we'll look at the table, and we want to do 5,200 psi, which falls between 5,000 and 6,000 psi concrete. That means that we're going to have to linearly interpolate, and that's what we did. I linearly interpolated between 5,000 and 6,000 psi concrete for a non-air and trained concrete mix. If I'm not adding air and training admixture, I have non-air and trained concrete. I just did this to simply not have to deal with putting in the admixture. Air and trainer is an admixture, and each product is different, so pretty much you have to figure out what air and training admixture you have and add it into the mix. For this entire mix, we're going to assume we're designing non-air and trained concrete. So just by performing the linear interpolation, I find out that my water-cement ratio for this mix is 0.466. once we have our water cement ratio, we can move on to step 3, which is finding how much coarse aggregate we need. Before before we can actually figure out the amount of coarse aggregate we need to make sure that the size of our coarse aggregate is okay. The size of the coarse aggregate really has to do with the spaces that the coarse aggregate will have to fit through in whatever we're going to pour the concrete into. So since we're doing a slab, I gave you the dimensions and spacings of the rebar. We need to make sure that the coarse aggregate will fit between the rebar and fit in the cover. On the right hand side, I've given you a table from your book which kind of tells you what the minimum clear distance between the coarse aggregate and the dimension need to be. So it has to fit between the forms, it has to fit between the rebars, and it can't be sticking out of a slab if you're pouring a slab. In our case, with all the spacings I gave you, our maximum aggregate size would have been 1.5 inches, but we're going to use number 57 stone, which is a fairly common stone, which gives us, which has a maximum aggregate size of 3/4 of an inch. So this will obviously fit, but it's important that you make sure that your aggregate fit into whatever you're going to pour. Once you make sure that your maximum aggregate size is okay, you can then use your bulk volume and the fineness modulus of your sand to determine your coarse aggregate factor. So our maximum aggregate size was 3/4 of an inch, which you see right here, and our fineness modulus was 2.8, so we can go onto the table and look it up and say our coarse aggregate factor is 0.62. If we take that coarse aggregate factor and multiply by the density of our stone, we can get the amount of stone per cubic foot of coarse aggregate, and that's what you have here. It's the 0.62 times the 107 pounds per cubic foot. That gives us 66.34 pounds per foot cubed. When we proportion a mix, though, we usually do it by the yard, not the cubic foot. So there's 27 cubic feet in a cubic yard, and that tells us that we need 1,791 pounds per cubic yard of our coarse aggregate. Once we've found our coarse aggregate, we can determine how much air we expect in our mix. So we're doing non-air entrained mix, so there's really nothing we can do about the amount of air we have in our mix, but we should end up with what this table tells us. Table 7.6 gives you the approximate target percent air content required for different nominal maximum size aggregates. And as you notice, it's approximate target. So what that's telling you is we really can't control this unless we start adding admixture. But for 3/4 of an inch non-air entrained mix, we should expect about 2% air content when we mix this. Once we look at the air, we can look at the workability. The workability has to do with how easily we can place the concrete where it's going. So we have different workabilities for different structures that we're building. So for reinforcing wall and footing, we want to have a slump between 3 and 1 inches. For a building column, we want a slump between 4 and 1. Building columns, you want a little bit higher slump because there's going to be more rebars in a column. There's going to be a reinforcing cage. You need to get, 1, the concrete down the column, and 2, the concrete in between all the rebar. So we look at the air, we look at workability, then we can look at the actual water content. So to figure out the water content, we look at table 7.8, which I've again found for you on the right here. From before, we were doing a slab, and our required slump was between 1 and 2 inches. We have 3/4 inch aggregate, so we look at slump 1 to 2, 3/4 inch aggregate. It tells us we need 315 pounds per cubic yard. If you look through the book, there are some reduction factors for using different materials, like if you're using river rock or any other kind of funny stone. In general, in the New Jersey and East Coast area, you're going to use angular crushed stone from a quarry. You're not going to be really dredging river rock and using that for cement. But now that we have the coarse aggregate, we have the amount of water, and we have a water-cement ratio, we can use our water-cement ratio to determine how much cement we need. So our water-cement ratio is 0.466. We know we're using 315 pounds of water per cubic foot. If we divide 315 by the water cement ratio, it tells us that we need 676 pounds per cubic yard cement. Now, there's a lot of checks you need to do on the cement based on where your concrete structure is located, whether it's going to be exposed to de-icers, sulfate in the soil, all kinds of different things. Over here I have table 7.9, which tells us the minimum requirements for cementing materials used in flat work, which flat work is anything flat where water can sit. We have 3/4 inch aggregate size, and we need a minimum of 540 pounds per cubic yard, which we meet. If you go down here and look at the bullet points, it will tell you if there's going to be de-icer, you need a minimum of 564 pounds per cubic foot. We meet both of those, so we're okay, and 676 pounds per cubic yard will work for our cement content. Step 8 in this whole process is admixtures. Now, admixtures come from different manufacturers, have different instructions, and do different things. So if you're going to add an admixture, being it a super plasticizer, an air entrainer, a retarder, an accelerator, they have their own directions and you need to follow their directions. And this is the point where you'd consider what your admixtures are going to do and follow those directions. Admixtures often are transported with water, so usually it's a very, very small amount, but you may want to take that into consideration if you're going to add a lot of one thing. It may affect the amount of water you want to add to your mix. And step number 9 is to determine the amount of fine aggregate. Now, this whole mix design is a volumetric mix design. So if you notice, we've been getting everything in pounds per cubic yard or a weight per volume. So what we're going to do is then design the mix for 1 cubic yard. We have all the other things we need, and what we're going to do is take whatever volume isn't taken up by the coarse aggregate, the water, the cement, or the air, and we're going to fill that volume with the fine aggregate. So what you see down here is I have my pounds per cubic yard of coarse aggregate, water, cement, and air. I can then turn that into a value of feet cubed per cubic yard by dividing it by its specific gravity multiplied by the density of water. So the specific gravity of the coarse aggregate is 2.65, and the density of water is 62.4, so I'll have 10.83 feet cubed per yard cubed of coarse aggregate. And I do that same calculation for water, cement, and air. The specific gravity of water is 1, obviously, but we divide it by the density to get feet cubed per yard cubed. Cement is pretty universal. The density of it is, or the specific gravity is going to be 3.15, almost universally. And the only thing you do different with air is obviously air doesn't weigh anything. So we're adding 2% air. So 2% of a cubic yard is air. There's 27 feet cubed in a cubic yard, so we're going to have 0.54 feet cubed per yard cubed. We add all of these volume per volumes up and get 19.85 feet cubed per yard cube. 1 cubic yard is 27 cubic feet, so he takes 27 cubic feet minus the 19.85 feet cubed per yard cube, and we find that we need 7.15 feet cubed per yard cube of fine aggregate. We can get the weight per cubic yard by taking that 7.15, multiplying it by the density of water and the specific gravity of the sand, and we find that we need 1,138 pounds per cubic yard of fine aggregate. After we get the amount of fine aggregate, the last thing we need to do is adjust for moisture. Now, knowing the amount of water in your mix is very, very important, and we saw that each of the aggregates had an absorption and a moisture content. So this whole mix was done in a saturated surface, assuming saturated surface dry conditions, which means that the aggregate has absorbed what it can but carries no more water. So if an aggregate is above the saturated surface dry condition, it's going to add water to the mix. If it's below the saturated surface dry condition, it's going to subtract water from the mix. And that's what you're going to see we're going to do a calculation for. Now, before we finally adjust for water, we need to make sure we get the right amount of aggregate, both coarse and fine. So we needed 1,799 pounds per cubic yard of coarse aggregate that was dry. But we know the coarse aggregate has 3% moisture content. So to get the correct weight of stone, we just need to increase the amount of coarse aggregate by 3%. So we take the 1,791 pounds per cubic yard, multiply it by 1.03 or increase it by 3%, and we need 1,845 pounds per cubic yard of coarse aggregate. The fine aggregate had a 2% moisture content, so we just increased the fine aggregate by 2%, so that we have the correct amount of coarse aggregate and the correct amount of fine aggregate. Once we've done that, we can adjust our final amount of water. We needed 315 pounds per cubic yard of water for our mix. From that, we need to subtract the moisture content held by the coarse and fine aggregate, but we also need to take into account the absorption of each of those aggregates. So what we have here is the moisture content of the coarse aggregate, which is 3%, minus the absorption of the coarse aggregate, which was 0.5%, and we have the same thing here for the fine aggregate. What happens if the coarse aggregate was completely dry? This would become 0, and this would be a negative times the negative, which would give us a positive, which means that if we use completely dry aggregates, we're going to have to end up adding water to our mix to account for it. If we use moist aggregate, the aggregate's going to add water to the mix that we then need to take out, so we'd add less than the required amount of water. And once we've adjusted the water, we've come up with our final mix design. For the final mix design here, we need 257 pounds per cubic yard of water, 1,161 pounds per cubic yard fine aggregate, 1,845 pounds per cubic yard coarse aggregate, and 676 pounds per cubic yard of cement. So that is how you proportion a mix design.